Hey everyone, thank you for coming to this special student seminar. We didn't think we were going to have another one this semester, but thankfully we do. And it's a really awesome topic. I'm excited. I hope you guys are excited. So without further ado.
Thanks, Lena. So today's talk is basically titled Fast and Replicable Deployment of Robotic Software, but it's not specific to robotics. So if you guys were, prepared for some ROS action, that's not what this talk is about. Sorry to disappoint you right from the beginning. This is a talk mostly about Docker and why it's a good technology to have in your toolkit. Because these days, given the way papers are being published and the way research is being done, it really makes sense to have a quick and dirty way to sort of start a new project really quickly, and a quick and easy way to share your project such that others are able to run it, right? And this goes not just for robotics, but also for things like machine learning applications, right? Where you need, like, I understand Google Colab is a thing, but there are times when you need a slightly more complicated workflow to share with people. So that's where Docker sort of comes in. And over the last 5-7 years, this technology has really sort of taken off. So I am trying to sort of give this talk because I use it on a daily basis for my research. And it would be sort of, it's nice to have more people on board, basically. So the first question is not what is Docker, but let's step back a little bit and ask ourselves, what is virtualization, right? Now, virtualization is something that has existed for decades, before probably any of us in this room were born. And it's a nice and easy way to make the most out of your system by sort of allowing multiple virtual computers to run on the same machine, right? And it has a lot of use cases, depending on who you are and why you need virtualization. That use case can change. But in general, it's a way to pretend as if every system, every virtual system is running on real hardware, right? So the virtual system does not know that it's virtual. I mean, of course, there are ways in which they do this, but for the most part, you can pretend as if each of them are independent systems. And more importantly, it provides what is called isolation, right? Each system does not know anything about the other systems which are virtualized. And more importantly, it does not know anything about the host, right? Which is the master computer on which everything is running. So for the most part, there is this concept called hardware virtualization, where imagine that you have a desktop and that desktop has certain resources, right? Now, these resources can be split up, partitioned, segmented, whatever you want to call it, and assigned to each of the virtual systems. And they are under the impression internally that that's all they have, right? They have no idea about the total available memory or network or processing power, nothing. They are happy with whatever they have been given, right? So this is the general structure. And the thing is, each of these virtual systems, because they're independent of each other, can run whatever they want, whatever software, right? So as I was saying, like, the host machine has certain physical resources, and you have this concept when you're dealing with virtualization, you come to the concept of a hypervisor, right? A hypervisor is basically a fancy name for something that manages all these virtual machines, right? And it's essentially like a driver that sits between the real system and the virtual system and assigns and sort of manages all these resources that have been allocated. And the other term is basically the guest machine, which is the virtualized system that is running. And it gets some portion of the physical resources, and it is able to run software independent of the host, right? And it gives you this logical separation from the host as well as the other virtualized systems, and it runs in a completely isolated environment, right? So this is how virtualization was done, or even now it's done, but these are the basic concepts that sort of underlie any virtual system. The basic tenets of virtualization is basically it provides isolation, right? And one of the ways you can use this is for security, right? Let's say you are a computer security engineer and you want to do what is called pen testing, right? You want to test if a virus is actually a virus, or you want to check whether a particular exe file, what does it affect on your computer? You are obviously not going to run that on your own system, because that could be a disaster, right? So what you do is you open up a virtual machine and you run the virus inside that. Just, so even if something happens, worst case, you close it. You close the virtual machine, you destroy it, spin up a new one, right? So isolation is something that's important, right? And safety, they sort of go together. The better resource use, I think, is also important, because when you consider servers, right? For example, one server running one OS, which runs 5 tasks, is a waste of resources because it's capable of running 10 times more, right? So it allows you to divide up your resources into independent systems and allocate them fairly, so that you can do more work from your hardware, right? And lastly, you come to the concept of snapshots, which is something that VMware, if you guys have used it at some point, that's what it was known for, is that you get one disk image file, right? I think, if I'm not wrong, it was called VIMG. Like, you take that VIMG file and then you give it to someone else, and they can spin up their own virtual machine immediately based on that. And it will contain all the data, all the files, whatever you had on your system, right? So it allows you to replicate, for one thing, and save virtual states. That's important. And it's a quick way to sort of bundle dependencies into one single file and share that everywhere, right? So there are a couple of benefits when you talk virtualization, and then depending on your use case, you're going to use all of these features or some of them. But these are all sort of the core concepts that, that brings up the need for virtualization. And the general structure is basically you have the individual VMs with their own apps, libraries, and the OS that runs on that guest machine. But below that sits the hypervisor, and your host can have an operating system or not have. That is optional. Now that gets into the weeds regarding virtualization, but you have the concept of hardware virtualization, where you don't have a OS, you just have the hypervisor which manages these things. And at the bottom, you have your physical infrastructure, right? Your physical network cable, your RAM, your memory, your GPU, whatever, right? So this is generally how VMs look, right, on an architectural level. That sort of brings us to, okay, what is Docker, right? The basic concept is that compared to a VM, right, you can imagine that when a virtual machine is started, you have to replicate every part of the system, right? Which includes the kernel, which includes, creating physical, a copy or like a clone or whatever of the RAM, of the CPU. All of these things need to be created, which causes a lot of overhead, right? It's for every VM, you need to have the same copy of all of these. And the funny thing is, like, if your host machine is, let's say, a Windows machine, right? And you have another VM that also runs Windows, you can sort of imagine that a large chunk of both of these things are going to be common, right? Between the virtual machine and the host machine. The question is it worth replicating everything? No, right? And this is especially true when you're running Linux-based systems, because most parts of the kernel, whether you're running, Ubuntu, or whether you're running Mint, or whether you're running CentOS, whatever, they all have the basic components of the operating system are generally common. It doesn't make sense to replicate everything. So that's something that a Docker container leverages, where it only uses the parts that are different. It only has to recreate the parts that are different. So, and basically it adds on whatever else is missing, right? So what are the benefits of Docker versus traditional VMs, it's fast because resource allocation is immediate. You are not having to recreate everything. You just tell them that, okay, this is what's available, take it. And isolation is happening, which is one of the benefits of VM. You do get isolation. The replicable nature, right, where you can save and distribute, that also exists, right? Because all the dependencies that you need are bundled, and you can have as many instances of them as you want, not an issue. And obviously, because you're not recreating everything from scratch, it's pretty efficient compared to VM. And of late, similar to how GitHub has happened, there is this concept called Docker Hub, where you can just publish your Docker image and anybody can just download it and run it, right? So distribution has also become easy, right? It's like an app store for whatever you want to publish. So the general idea of what's a VM versus container is sort of quickly described by this, where you have the virtual machine, as we saw, is that you have separate everything, right, from the ground up. Whereas in case of containers, you have Docker sitting there, which you can think of as an analogous to to the hypervisor, which manages this resource allocation and management. So not just the allocation of resources, but also, is someone trying to exceed the resource limit, right? Things like that. And you have the host operating system. Generally, it's Linux-based. And at the bottom, you have your physical infrastructure. And you can see that all of these apps that you run, they don't rely on anything else. They just run because all the kernel related and the libraries and the dependencies are already present. So any particular questions so far before we move on to slightly more in-depth stuff? All good. Are you guys, just a quick maybe show of hands, are you guys familiar with Docker? Have you used it on a daily basis? Okay. So yes. Yeah. Okay. So let's then dive right into the deep end of things, where we try to at least go through the low-level concepts of how it works, right? The thing is, Docker or any other container-based method, it's not new, right? The Linux kernel already provides you with ways to do these things. It's just that what Docker does is it packages everything into a nice little bundle that you can sort of type a few commands and get running. So let's see how it works, right? So in Linux, there is the concept of a kernel namespace, right? Kernel namespaces basically allow you to segregate processes, among other things, into their own logical separated sort of boundary setup, right? So you can say that this process and all its requirements will go under namespace A, right? And that includes everything from the process ID, the file systems that it can mount, the networks that it's exposed to, the user ID, host names, everything. You can sort of split off from the main system and put them together in one group. And that is the essence of what Docker does. It just does it in a clean, neat way. But what I'm trying to say is that these concepts are built in to Linux itself. Basically, what namespaces do is that it allows the kernel to have one set of processes, only see specific sets of resources, right? It internally does that at the software level, essentially. So how does it do this? The thing to keep in mind is that there are different types of namespaces depending on what resource you're trying to access. So let's go over a couple of them. One of them is the UID namespace, right? Which means that a process does not need to have access to all the users that are available on the host machine, right? It is isolated from the rest of the user ID tree that runs. So the benefit of this is it allows you to have root access, but only within that namespace, which sort of ties back into our security and isolation concept that we discussed, right? Because you don't want any program to get root access to your system ever. So, but in a container, maybe it's fine. So UID namespacing allows you to do that, right? The other thing to do is the PID namespace, right? Generally, when you turn on the system, right, any Linux-based system, it's going to make a tree, right? It's going to make a tree where you have process IDs, right? Generally, the first process ID, PID1, for the most part, is systemd, which handles the boot up and the initial startup and everything. But that tree you can have for a PID namespace, you can have a separate, right, which only contains the PIDs for that container, right? There's no back and forth between the two trees. You can have network namespaces where you have a network on your host computer, but you can create a new virtual network, maybe, right? With limited IP addresses, limited routing tables, access to very specific sockets. You can do all of that using a network namespace. Similarly, there are mount namespaces and IPC namespaces. I am not going into too much detail into these, but the essence is the same. IPC stands for inter-process communication. And what IPC namespaces allow you to do is basically say, okay, this guy can communicate with so-and-so set of IPC instructions. So these are pretty high-level concepts, which you're not exposed to on a day-to-day basis. So let's just leave it, but it exists. Okay. So the idea that I wanted to sort of bring up is that these individual concepts, when brought together into one system, acts as one virtual system, right? All of these together give you the impression of having a completely isolated network. That's an isolated machine, right? Which is a container. So these can be used independent of each other, or they can be used together. That's the idea. Okay. So let's look at the real, like the actual commands that actually, gets this done. There is a command in Linux. So these are all terminal commands, basically. I mean, shell commands. So there is the command called unshare, right? Which is responsible for creating a new namespace, right? Again, these are not things that you will need to do manually ever, but it's good to know, right? It gives you a sense of how it works inside, under the hood. So you have the unshare command, which is responsible for taking a process and sort of putting it into its own namespace. And how do you list the namespaces? You do that with ls-ns, right? ls, if you're familiar with basic Linux, is list, right? And ns stands for namespaces, essentially. The other thing that a Docker or any other container system, so Docker is, by the way, Docker is not the only one. Just to be very clear, there are others. But we are taking the example of Docker because, it's popular and it's what I use. So another main thing that your container management or engine is supposed to do is handle C group commands. C group stands for control groups, right? Which there is this trope, I guess, in Linux where everything is a file, right? Even your memory is a file, right? Everything in Linux is a file. And what you can do with a container management engine is that you can say that, okay, make a new file which corresponds to, let's say, the memory allocation, and say that, okay, this is the hard limit. And that's basically what's happening here. So you would want to do, you create this file, right, which is a new control group called foo. And then you say that, okay, 50 MB is all that this control group is allowed to access. That's it. Obviously it's more complicated in person, but this is what your Docker engine is doing when you start a new container, right? And it handles this automatically, right? And so you have very similar commands. Basically, you create one of these control group files and then you assign whatever you need. So you have the same thing for CPU. You can say that, okay, I don't want to give it more than 2 cores, let's say. And it allows you to handle IO. It allows you to handle networking, all of them using very similar commands, right? Every time you start. And these commands are generally standardized for the most part. So if you want, you can go ahead and look up the source code for, a container management engine, and somewhere you would find something that looks like this, pretty much. So, okay, quick little sort of comic that I really liked on what are Docker file systems, right? Because as I said, everything in Linux is a file, right? So it makes sense that your Docker container would also be based on a file system, right? Now, you don't have to go like too deep into this, but basically what it's saying is, we discussed that Docker containers are fast, right? So how is it fast, right? It does that using this special overlay file system, right? So you've heard of NTFS, right? That's a file system. You've heard of FAT32. That's a file system. You have heard of, I don't know, what else is there? ButterFS, for example. That's also a file system. There is something that's similar that exists, which is called an overlay file system. And this is what allows Docker to do the non-repetition part that we spoke about, right? Where you don't need to replicate everything from the ground up, you only merge the changes. And that's what basically what this container is, like what this code is saying, is that you have the concept of an upper and lower directory, right? You have the concept of an upper and lower directory, and each of these upper and lower directories have specific capabilities, so to speak, where we have this concept of union file systems. So OverlayFS is a new one. There used to be something called AUFS before that. Again, these are all built into Linux for the most part. Docker is just putting it together. So you have the concept of the lower and upper directories, where lower is basically read-only. You cannot write to it, whereas the upper layers have ways to read and write. So when you have such a file system, how do you read and write? You read from the upper directory first. If the file is not available, then you look at the lower levels one by one, right? How do you write? Just write to the upper directory, because you anyway can't write to the lower ones. So Docker engine handles all of this, and we'll come to the details, but when you build a Docker file, right, into an image, that's essentially what it's doing. Every command that you have in your Docker image, in your Docker file, is one directory. And whatever is common stays. That's how it builds up the whole structure. And that is another reason why it is important to make sure you try to be efficient when you're writing your Docker files, because the more layers, the more directories it needs to create, and that is an overhead. So that's where this comes from, is that people, like, if you see, the best practices always say, keep your layers to minimum, and this and that. This is why they say it, because every time it adds, right? So unpacks, basically the Docker engine, it unpacks each layer into its own lower directory. So you can have multiple lower directories, as in every time you add an upper, the previous upper is now the lower directory. That's what happens. So again, there are a couple of scenarios depending on what you're trying to do, so let's look at the read scenarios. So let's say you want to read a file that does not exist in the upper layer, right? So what do? You read from the lower with very little overhead, right? You just have to go down one level. Let's say the file only exists in the upper layer. You can read it directly from the upper layer. And in the case that it exists both in the upper and the lower layers, you read the version from the upper layer. And generally what happens is, like, I'll show you a demo about this in 2 slides actually. What happens is, if the same file exists in the upper and the lower, the upper layer basically is the one that is given when you read it. It masks the value in the lower layer. So it's like an update. Whatever comes after, that's the one you get. Similarly so the write scenario is a little complicated, right? When it's a first time write, and this is what I meant by be careful when you write your Docker files, because if the contents of a layer hasn't been seen before, which means that you're adding way too many distinct commands, you have a first time write, because that doesn't exist. That upper directory does not exist anywhere. So what happens is, first, The first thing it does is it does a copy up operation from the last lower to the upper. And now you can write to the upper, right? And copy is not like copy happens for the entire file, right? Everything, the entire directory has to be copied up. And for larger files, it's a performance hit, right? It takes time. But obviously, this penalty happens only the first time, right? So after you have written, if you've done this copy up operation once, it's fine, right? It'll always go to the copy thing. When you delete, what ends up happening is there is a special file called a whiteout file that is created in the upper directory. And what it does is it blanks out the same thing on all the lower directories. It blanks out the file in all the lower directories. That's how it deletes, right? And the same thing for directories, but in this case, the special file is called opaque. For renaming, right? Because again, this file system is what you get, right? Once you build your thing, you get a file system, right? You want to perform these kind of operations. What ends up happening is the move command only works if both the source and the destination file exists in the upper layer. If it exists in the lower layer, it cannot traverse between layers, essentially. So both the files that you want to, so move basically, like that's how you rename in Linux-based systems, right? You do MV, you put the old name and the new name, right? So both of these have to exist in the upper, otherwise it doesn't work. So, okay, any questions as such so far? We'll get into sort of practical demo, but any issues so far? Okay, so simple set of code. So it's better if we just run the demo. Okay. Let me, yeah, so this is how I watch my lectures. So let's pause here for a minute. You have 4 directories, right? Let's say we create, yeah. So we create 4 directories first, right? Upper, lower, merged, and some folder called workdir, right? And that's what we get. So we can see that we have all the 4 directories. Let's create a couple of files, right? The first file we'll create is called upper text, right? And we put some text into it and we store it in the upper directory, right? So we have 4 directories. We create some random text file and then we put it in upper, right? We do the same thing for lower. We do the same thing for, yeah. Man. Okay, so we create another file lower in the lower directory. Now comes the crucial thing. We create one file with the name both in the lower directory, and we create the same file called both in the upper directory. And the reason for this is we want to show what happens when you have duplicates, right? In both the upper and the lower directories. So, okay, so these are the 4 directories, and then we can see that we have all the 4 files in the right place. Okay, so we have this is an upper in the upper text, we have both in the upper, and similarly, we have the same thing lower. Now, what we do is now comes the main command, which is we use the OverlayFS file system driver on Linux to specify that, okay, what is the upper directory, what is the lower directory? We give the paths, and then we say that, okay, where are we going to mount it? We are going to mount it in the merged directory. How many of you are familiar with how sort of mount points work in Linux? Like, are you guys okay with that, or I can? Okay, so mount points, again, because everything is like a file, generally what ends up happening is when you want to access the file system of a particular drive, the operation that you use is called mount, right? And that mount happens to a specific directory. It's called a mount directory in Linux. And essentially what you end up doing is you say that, okay, this particular file system gets placed at this directory structure. That's what happens. And the way you do that is with the sudo mount command. The specifics of the command are not too complicated in this particular. So for different file systems, you have different parameters. For the overlay file system, it needs 3 parameters. One of them is the directory for the lower dir. One of them is the directory for the upper dir. And one of them is some work dir where you have some temporary space or whatever. And the last thing that you do is, where are we going to mount it? So that's what you get here, right? This is the random directory we had created, the merge directory. Okay. So now we can see that if we try to access the common file from this merged overlay file system, we are going to get the data from the upper layer. And that's what I meant by masking, in the sense that the OverlayFS automatically says that only the common file, the copy of the common file or the version of the common file that exists in the upper layer is going to get shown. Okay. So yeah, and you can see that in the merged directory, right, you have lower text, you have both, and you have upper text, which means that only one copy of the common file was stored in the merged directory. And internally, it maps to the copy that exists in the upper layer. That's important to know, because this is the core concept of how you build a Docker file, basically. Okay, so yeah, so we are done with sort of the deeper details. Now let's go into the specifics of how you use it in practice. So you have the three main things, right? One of them is the Docker file, one of them is the image, and one of them is the container. Now, a Docker file, I like to think of it as source code for what your environment is going to look like, right? It basically says that, okay, what OS you will have, what files you will have, what's going to be installed, what packages, everything, right? But by itself, it's just a text file. It doesn't do anything. You then take that Docker file and you compile it using Docker build into an image, right? Which contains the final system that's going to be deployed, right? I don't know how many of you are old enough to know about ISOs, but then when you legally obtain an ISO at some point and then you try to run it, that's what an image is. You can't make any changes to the ISO. It's just you double click it and it works, right? And then the app that gets run, right? You can think of that as the container, right? So you take an image and then you deploy it, and that's what a container is. It's one running instance of the image. And obviously you can have as many of these as you want, and they will be exact copies of that image. You make whatever changes you want, but by default, there is no guarantee that it's going to be saved. A container is, you should always make the assumption that the data inside the container, it disappears the moment you shut it down. It's as simple as that. There's no storage by default. So whatever application, that's why it's good for running demos. You can imagine that a demo is only supposed to do one thing, right? You run it, it shows you the output, and then it shuts down. There's no question of storing, saving, whatever data. So that's why Docker sort of has become more popular, because you can do one thing and one thing properly. A little more detail on what a Docker file is. It's basically a set of instructions needed to build the image. And it's not a very complicated thing. It's just essentially a set of shell commands that get baked into the image, right? And when that image is built, all of these commands are basically executed and you have your operating system. And you use Docker build as we spoke. And you have a couple of specific commands that Docker files can understand. And this is sort of a very non-exhaustive list, right? So you have the from command, which says that, okay, this OS contain this image that I'm building, what is going to be the base operating system for that? So that's what you set in the from. You have the run, which essentially says that, okay, run this particular command in a shell of your choice inside the image when you're building the image. The env sets environment variables, right, which can be accessed by the run variable. Whenever you run something, you might need environment variables. The env sets that. The cmd is useful when you want to launch something when you run a container, right? So from time to time, let's say your demo, you need to launch Gazebo, for example, on startup. That's what you set in cmd, right? The add and copy, they are slightly different. We'll go over the differences in the next slide, but basically what they do is they copy files, directories, whatever, from some file system, generally the host file system, into the container, right? So let's say you have large files which exist outside. You don't want to sort of manually copy everything. So you use the add and copy to put things into your image. And the work dir is sort of the last thing, which says that, okay, before you run any command, it's like a cd command, right? It's a change directory command for everything that comes after. So if you set the work dir to home user at the beginning, every command that runs after that will run relative to that work dir directory. And obviously you can switch as needed. Okay, so quick note on add versus copy. Basically, add has the added advantage of doing extraction of compressed files. So if you try to upload a zip, it'll decompress it and put it there. It also allows you to copy files from remote sources, right? So you can give it, let's say some text file exists on some server, you can give it the URL and it'll get that for you. But it's not good, right? These kind of functionality is a security risk because now you're opening up more and more avenues of attack into your system. So and it's unpredictable because there's way too many things going on with the add command. So the best practice currently is that use copy, right, which only allows host file copying, host system copying, and whatever you need from remote, write an explicit wget command so that you are in control of what gets executed, right? Because when I say run a wget command, you are in charge of that command, right? You know what you are asking it to do. So that's the current best practice. Let's see how to build a Docker file. This is the general command where you just do Docker build and then you pass in a bunch of parameters. And this is sort of the simplest set of parameters that you will need, right? The first thing you do is you may or may not specify the Docker build kit environment variable. What that does is it uses the new build kit engine that Docker has released. Bunch of benefits use it. Docker build is the main command that builds the thing. -t image name is basically the tag of that image. It specifies, it's like the name of what gets built, right? And you will use that tag to specify that image later on. -f is the path to the Docker file, which says that, okay, this is where it exists. And the dot is basically the build context. Next slide, quick note on what the build context is. From time to time, you might want to rebuild everything from scratch, right? As we said, the overlay file system, it does not rebuild things, right? It has a cache of everything that has come before it. But let's say that you've made certain changes which requires you to rebuild everything from scratch, right? You use the no cache. And lastly, you have the -- pull, right? So this generally functions on the base image where it will always pull the latest version of the base image when you build it. That build context basically says that every operation that requires you to have access to files on the host happens with respect to that dot. So that dot means this folder. You can set it to other locations, but just keep in mind that you have taken everything into account, right? All the files and all the copy and add or whatever you do inside your Docker file is going to happen with respect to the build context. So most people, like, it's very easy to miss that dot, right? I mean, it's just a dot, but that's part of your command. You have to have that. Okay. So Docker images, you do the Docker build, and then you sit and wait for it to build, right? And then you can do this Docker images, which is, you have a couple of commands, which is, you can't do anything once an image is built generally. You can just list it and get information about it. And that's essentially what these do, right? It allows you to look at all the images that exist on your computer. It allows you to filter by name or tag or whatever. And it allows you to have the full names. So these IDs that you can see, image ID, this one, these are the short forms, right? But sometimes you might want to see the long form, and that's what no trunc does. It gives you verbose information. Now comes the container, right? Which is the main running instance. So you have an image now, you want to do Docker run. Now run is internally two separate commands. One is the create and one is the start, right? So couple of commonly used options, which is the -d, which means detached mode, where it starts the container and puts it in the background for Docker engine to manage. Otherwise, whichever terminal you execute it in, it's going to keep running in that. So generally, you might want to put it in detached mode. The -i basically says that, okay, where do I want to see my outputs? std in, std-air, and std-out, right? These are the three output options. -t says that it allows you to have a terminal access, a shell access that you can use to communicate with the container. Because again, the container is a virtual system, right? It only has access to what you tell it. So there's no way to talk to the container unless you put in the -t, right? Which says that attach a TTY terminal to that process. And generally you combine this I and T into one -it. And that's what you pass. We'll see a full command in a few minutes. You give the name of the container. Again, this has to be unique. We have the -rm, which means after you exit the container, delete all trace of it, right? Delete all the layers that you've created and restart, right? Which says that, okay, if the container crashes, what do you do? Docker networking, again, couple of types. I'm trying to sort of not focus on the unimportant things, but there is a way to create different types of networks on which your containers run. So you have the bridge network, which creates your own isolated network within which all Docker containers connect to each other. You can, and that does not give you access to the host, right? You get access to the host network using the second mode, which is every container directly connects to your system's thing. So IP addresses, everything is the same. So the others, there are a couple of them, but not used commonly. So for the most part, day to day, you will use the bridge and the host mode. And they are all different given the circumstances. Why is this important for ROS? Is that when you have 50 robots all trying to talk to each other on the same network, the host networking makes it easy because your computer, you just assign whatever static IP you want, and then your container-based application can access that. And because ROS is on the network, you can discover every robot directly, right? And that's the practical use case of networking. Quick note on GPU usage. Generally, when you have virtual machines, you cannot access the GPU because a virtual machine cannot access a part of your GPU. It either needs it all because it's the whole thing, or you don't get anything. But with Docker, with containers, because again, everything is a file, everything happens through files, you can give shared access to that file that controls the GPU. and your host talks to the GPU on behalf of the container. So you can now have one GPU being used by 20 containers through the file system thing. So the way you do it is NVIDIA, as an example, gives you its own runtime, right? And you just tell Docker that, okay, I want this to run with the NVIDIA runtime. And that's it. So now you have access to the GPU for deep learning applications, for example, or graphics, right? So quick, super fast ROS demo. Let's take a look. Okay. So you have a couple of images. Let's wait. Okay. So I'm building a ROS image on the top left terminal, as usual, Docker build, right? I call it ROS image. Now you can see here that I have the ROS_image repository, right? Which means that I have that image created. Now, the next thing that I do is I create one container from this image with the name ROS container one. Okay, and the parameters that I'm passing, we have just discussed, right? Basically, it gives you the -it, -d. It specifies the network to be the host network. And the last thing I do is I specify which image is going to be used, right? Which is the ROS image. Let's create that. In the others, on the top right, I create a new terminal. I create a new thing called ROS container one. It will give you an error if you try to create two containers with the same name, right? So that was just a typo on purpose to show you that it will give you an error. So now that I've renamed it to ROS container two, it's going to create two separate containers for us. Okay, so now I do the Docker run. So now I have two separate containers. Here you have ROS container one and ROS container two, but you can see that the image they're derived from is the same. They're both from the ROS_image. Okay, so now containers are running. What I do now is this line basically says that take Docker exec, which means execute, -it, right? In interactive mode, execute with the user. So in this case, -u stands for which user do you want to execute that process as, right? So in this case, the user is called user. And then I give the name of the container and I specify what program I want to execute. So in this case, I want bash, right? I want to run bash in that container. That's what this means. And I want to run it as the user. So same thing on the right. So now top left, I have one bash running in container one. Top right, I have bash running in container two. Now I'm just doing the same thing. So the left-hand side is container one, right-hand side is container two. On the left-hand side, I have launch ROS core, as I normally do. Again, if you guys are sort of familiar with ROS, this should make sense. I'm publishing on container one a test string, right? Now I go to container two, and then I try to list it. You can see that the topic exists, and more importantly, I can view that. For all practical purposes, this could be two computers on two separate networks. It's that easy to set up 50 containers running ROS if you have one ROS image with you. That's it. You can have as many of these as you want. They're all on the same network, right? So as long as your computer and the other computers exist on the same network, this is it. You're done. So that's essentially what it is. And this is a quick sample of the Docker file that was used to create the thing. You can see that it contains all the keywords that we spoke about, right? From, env, workday, run, cmd. It contains all of these things. And these are all bash commands, as you can see, right? Standard bash commands. This is what a Docker file looks like. That's it. So this will give you a working ROS system. This Docker file, when built, will give you a working ROS system. Last thing to keep in mind is a volume mapping, where we told that it doesn't save anything once it's killed, once a container exits. So in that case, what you do is Docker provides a way to securely, so to speak, access the host's file system from inside the container. There are two main ways to do it. One of them is called bind mapping, and one of them is called volumes, right? The main difference with them is that volumes are sort of internal to Docker itself. So you as a host cannot access that, right? It's sort of opaque to Docker. But bind mounts gives you a one-to-one access between your directory on the host into some specified directory inside the container. And this is something that I use on a daily basis when you're working with ROS, is that ROS has a very specific directory structure, right? You have the SRC, you have the workspace folder. Inside that, you have the SRC, and then you have your multiple packages, right? Now, when you are working with a ROS container, you might need to create a new package tomorrow, right? So again, this is my personal preference. It works for me, but it might work differently for you. But what I do is on my host, so on the left is the host, I make an SRC folder, and then I just create all the packages in that. And then I map the entire SRC folder of my host to the corresponding SRC folder inside the container. And now the thing is, what I can do is I run the container, but I have my editor, VS Code for people who use it. So I run VS Code on my host. I am modifying files on my host, but because it's volume mapped, the changes show up inside the container. And that makes ROS development really easy. I'm compiling code like cat can make, I am doing inside the container. Let's not forget that. But the general editing, you don't need to install all of these things inside your container, right? Because again, the more things you add, the bulkier it gets. Don't need to do that. You edit natively on your host. But because of the volume mapping, it shows up inside. So that's my setup. It's just something that you might want to use. The other thing that I use on a daily basis is Portainer. Very popular UI, web UI for managing Docker, right? You can manage every aspect of Docker through commands, but Portainer gives you a way to manage Docker within Docker, right? Portainer itself runs inside Docker, but it provides you with a nice little thing. What's it called? Provides you with a nice little web UI, right? I have a demo, but I think I'll leave the last 5 minutes for questions or something. But it gives you a nice little web UI to operate Docker using GUI. You can click, you can point, and you type out things like you would. You don't need to run all of that Docker run this, that commands. No need, just do it directly in Portainer. So yeah, that's basically what I have. Feel free to ask any questions, and I'm right here to answer them.
Hey Kanishka, this is Utsav.
Yeah, hi.
It was a great talk. So I have a question regarding like the various Ubuntu versions. So let's say some of the robot drivers which are not available for newer ROS versions. So you have to compulsory use Indigo. In that case, if you're using Ubuntu 20 on the host machine, can you build those packages on kernel which is using Ubuntu 14?
Yeah, I mean, that's a very good question. And you've sort of hit the nail on the head in terms of why I like Docker, is because it doesn't matter what version of Ubuntu you're running inside your container. You can run 14.04, 18.04 on a host OS that is running 20.04.
Okay, so kernel versions don't match. Like if the kernel versions don't match, that will still work.
It will work because it will take the delta between what you have and what is needed.
Okay, thanks.
Anyone else?
So how do you provide hardware access to ports and other things?
Ports, again, because if you use the host networking, ports are accessible anyway. But if you want a simple example of how someone exposes ports, you can see that this -p is how you expose ports. If you don't use host networking. So if you don't use host networking, by default, all ports are closed. But if you say that, okay, -p 8,000, 8,000, what that says is 8,000 port 8,000 on your host is mapped to port 8,000 inside the container.
And with what USBs?
When you run, there is a special device tag. So you can access cameras, LiDARs, whatever, just by saying that, okay, again, everything is files. So it's a file mapping. That's it. Yeah, all of those is part of the Docker run command. Yeah, who else? Okay. I think we'll end it here then. Thanks all for attending.